Let's quickly review emission. Seen here is an atom with different energy levels or orbitals. The larger the radius of the orbital, the higher the energy level and the more electrons it will hold. The red represents electrons, while the greens are spaces where more electrons could fit in order to fill the energy level. The blue is a higher orbital which is not yet filled. In order for an electron to move to the blue orbital, excitation energy is required, which comes in the form of light energy, collision energy, and chemical energy. Electrons can only absorb the specific amount of energy required to move from one energy level to another. If the energy provided is not this value, the electron will not absorb it. Here is a photon which contains the correct amount of energy to excite the electron. The electron absorbs this energy and moves to the higher blue energy level, leaving an empty space in its old orbital. It is energetically unfavorable to remain in the excited state, so the electron will emit the energy it absorbed in the form of a photon or vibrational energy, sending it back to the ground state. The experimental goal was to determine what factors emission intensity is dependent on. According to the hypothesis, emission intensity is completely dependent on energy input and independent of the emitting substance. Emission intensity is the number of photons that a substance emits within a given period of time. The higher the intensity, the more photons are emitted and the brighter a substance will appear to the eye. The dye and activator molecules react chemically such that energy stored in the activator reaction is transferred to the dye molecule. Seen here is our prediction for if energy input was the only factor that affects emission. For the red and green dyes, the lambda maxes would fall at the same intensity because the ratio of activator fluid to dye was the same. The wavelengths of each peak correlate to their visible color. Meanwhile, the 1:1 mixes of the dye has two peaks which fall at the same wavelength as red and green but only have half of the intensity in order to total the same intensity as the individual red and green peaks. The emitting substances in this experiment were the red and green dye and the 1:1 mixture of the two. Each dye emitted different wavelengths of light depending on their molecular structure. Green dye emits at approximately 510 nanometers, while red dye emits photons at approximately 620 nanometers. The 1:1 mixture emits photons at both of these wavelengths. The green dye emitted more photons than the red dye, which combined with the same amount of activator. This occurs because the excited electrons in the green dye molecules return to their lower energy levels faster than in the red dye, freeing dye molecules to become excited again, and thus producing more photons in the time of measurement. Meanwhile, the mixture would have two peaks with a higher intensity in the red peak, as seen in the data from the previous video, because less energy is required to excite the electrons in the red dye than needed to excite the electrons in the green dye. Thus, a given amount of energy will produce more red dye electron transitions and photons than green. The electrons in the red dye have the possibility of being excited by the photons emitted by the green dye, while the red dye emissions contain too little energy to possibly excite the electrons in the green dye. Imagine there are two students. After a sip of coffee, one student feels more alert while the other does not notice the difference. After drinking the whole thing, both students feel the effects. Student 2 is shaking while student 1 feels alert. Student 2 correlates to the green dye while the reaction correlates to intensity. The higher the energy input the student/dye had, the more of a reaction/intensity that occurred. Student 1 is the red dye, as with the same energy input, they displayed less of a reaction intensity. Our results from changing the ratio of activator to dye show that the amount of energy input still has an effect on the overall emission. When given less activator, the dyes displayed lower intensity and vice versa. Our results disproved our hypothesis and show that the emission intensity is dependent on both energy input and the molecular composition of the emitting substance.